I'm going to solve the same problem, but this time I'm going to use the angle phi as the variable. So let's just go over the steps again. So we have, this is the current carrying wire, it's carrying current I. Instead of choosing the x coordinate as my coordinate, I'm going to choose this angle phi as my coordinate. Right, so I'm going to express everything in there. So let's just notice that I'm just parameterizing the points on the circuit by this variable. So as a result, this point on the circuit has coordinate phi, which means this point in here on the circuit has coordinate 0. This corresponds to phi equals 0. So as a result, if I go to the right end of the wire, you can see that that angle becomes 90 degrees. So therefore, the 90 degrees is the maximum. So phi is less than 90 degrees. Cannot be equal to, but of course, this is going to be the limiting value. And I know that since this point corresponds to phi equals 0, anything to the left of that point is going to have a negative phi value. So as a result, this point in here is going to have a coordinate phi which is negative, which means when I go to the far left, I'm going to reach to minus 90 degrees. Right. Let's remember that whenever we do an integration in angles, we always use the radian unit. This is the natural unit. So as a result, I'm also going to write this thing down in terms of the radian. So it is therefore a quantity that takes on all values between pi over 2 and minus pi over 2. I can even write equality in here because that's going to be the limiting value. So the integral will be between minus pi over 10 plus pi over 2. So we choose our coordinate. It's well defined. So we then divide the wire into small segments and identify all the variables. So in this case, it is useful to remember the old variable in here, x. We can express x as r times tangent phi. Right? Just remember that in this expression, r is a constant. So as a result, the only variable in here is the variable that I'm going to use. It's the phi variable. So that's basically what I'm going to do for any kind of other variables. Express every other variable in terms of phi variable, right? So this is the x coordinate, and I would like to actually obtain an expression for the length of the segment that I'm considering. That's dx, but that can be expressed by using the derivative. So that's just calculus actually. So let's remember this expression, dx is equal to the derivative of x with respect to phi multiplied with d phi. So therefore dx is equal to r divided by cosine squared phi d phi, right? So that's the one of the expressions that I'm going to use. Another one is the distance of my point to the line segment in here. So it doesn't matter whether I take that distance or this distance or the distance to the midpoint. They are going to be more or less the same. Just remember that this dx distance is infinitesimal. I'm going to take the limit where this thing goes to 0 at the end. So as a result, for this case, it doesn't matter whether capital R is defined in either way. So in all cases, we are going to get the same value. So therefore, r is equal to little r divided by cosine phi. All right. So then let's get to the next step. So express the magnetic field produced by the chosen segment. So we know that the magnetic field is at this point is out of the board, and it has a z component. I called it that dBz. That is if you just write down the Biot-Savart law, so this magnetic field is equal to mu 0 I divided by 4 pi. Length of the segment is dx. There's a cosine phi angle coming. We have discussed all of this, and then this is an inverse r squared relationship. So what we need to do is to write everything in here in terms of phi and simplify it. So if you do all the simplifications, then you are going to see that the z component of the magnetic field is something multiplied with cosine phi and the d phi. So this is an expression that can be integrated easily. So then we can pass to the next step, integrate the components of the magnetic field. So let's just write down the integrals in here. So I'll just start from here. So dBz, let's repeat the same argument. So mu 0 I over 4 pi r. These are all constant quantities. And we have an integral of cosine phi. And let's just write down the integration limits. So that's minus pi over 2 and plus pi over 2. So the integral is sine phi evaluated between pi over 2 and minus pi over 2. And I know that this is equal to sine of plus pi over 2 minus sine of minus pi over 2. That plus pi over 2 has a sign which is plus 1, and the sign of minus 90 degrees is minus 1. So as a result, our expression is 2. So from here we can then deduce that the z component of the magnetic field is equal to mu 0 I over 2 pi r. I'm sorry, I forgot to put an integral sign in here, so let's put this thing as well. So in short then, if I have a wire, an infinite wire that carries a current I, then at any point in space, which is at a distance little r from the wire, there is going to be a magnetic field, at least for the case where the point and the line within the plane of the screen, this magnetic field is pointing towards us, and it has a magnitude given by mu 0 times the current divided by 2 pi r. Later when we see the Ampere's law, of course, we are going to see that this expression can be expressed in a very simple way so that it will be impossible to forget about this expression.